Writing Lewis dot structures. Well, molecules actually have shapes, and the shapes are determined by the number of atoms that are attached and a number of things called lone pairs. And to get to that point where you can tell the shape or the structure, you have to be able to sketch out how things are attached. And that's the whole purpose of the Lewis dot structures, to kind of give you an idea what the shape is. And so let's just start with a simple molecule. Let's do CF4. There we go, carbon tetrafluoride. Tetra means there's 4 fluorines attached. This is carbon tetrafluoride. And by the way, Lewis dot structures are only for covalent molecules, not ions. And so the first step is that you should add up the valence electrons. And where do we find the valence electrons? Well, we find the valence electrons on the periodic table. And you look and you see, it goes 1, 2, 3, 4, 5, 6, 7, 8. It's the same as the group number. And so we have carbon tetrafluoride. And so carbon is in the group that has 4 valence electrons, and fluorine is in the group that has 7 valence electrons. So we would say for carbon, we have 4 valence electrons, and for fluorine, we have 7, but we also have 4 fluorines, which gives me 28 valence electrons for the 4 fluorines. And so if we add them up, we get 32 valence electrons total. Now, be very careful. The valence electrons are the outermost electrons, which means that it's not all the electrons. It's just the outermost electrons. And so we have 32 valence electrons. And so what we have to do is we're going to have to put down electrons up to 8 around the different atoms. So everyone wants 8 electrons except hydrogen, which is happy with 2, and boron, which is happy with 6. Okay, everybody wants 8 electrons. And so the next step is we're going to take whatever atom is by itself and we're going to put it in the middle. There's carbon. It's by itself. And it doesn't matter if it's the first atom or the second atom. It just needs to be by itself. And then we're going to go north, east, south, west with our 4 fluorines. Now, if you don't have 4, if you have 3, you only put down 3. If you have 2, you only put down 2. And so what we're going to do is we're going to put down electrons and we're going to do a running total. And so a bond is 2 electrons. Okay, a bond is 2 electrons. So let's go ahead and make a bond for each one of these fluorines. And so we go, here's one bond, there's 2 electrons, there's another 2, there's another 2, and there's another 2. And so we have bonded on the fluorines. So we're going to glue on the atoms on the outside. And we just put down 8 electrons. So what we'll do is we'll subtract off 8, and that leaves me with 24 electrons. And it's very important to keep track of how many you put down, because you don't want to put down too many, more than you have, and you don't want to put down not enough. We need to use up all 32 electrons. So now that we've glued it on the inside, let's go ahead and put down up to 8 total electrons around the outside atoms. Now, right now, each one of these fluorines has 2 electrons attached. So we have room for 6 more on each one of the fluorines. And there's 4 of them. And so since there's 4 fluorines and I can put 6 electrons in each one, 4 times 6 is 24. And so I can put down 24 more electrons and have none left over. And so I go 2, 4, 6 on that fluorine, 2, 4, 6 on that fluorine, 2, 4, 6 on that fluorine. And the final fluorine, we put down 6 more, and that gives me 24 electrons that I just put down. And we go ahead and subtract them off, and we're left with 0. Now, the next step, and that was step number 2, is we'll go ahead and do that. And the final step here is we need to check for octets. Octet just means that we have 8 electrons around each atom, except for hydrogen, which is happy with 2, and boron, which is happy with 6. And so I look and I see that I have 8 electrons around each one of those fluorines. Now, the bonds are actually being shared, so we can see that around the carbon, we also have 8 electrons. And so I'm just circling this to show you, that sure enough, there are 8 electrons around those. And then we would say, well, that's carbon with the 4 fluorines. We can replace the bonds with lines, a line representing 2 electrons. And this is the structure. And many times we'll leave off these non-bonding pairs. That's what those extras around the fluorine are called. They're called non-bonding pairs. And if we look at a table of shapes, we would say that this is 4 bonded atoms and this thing is tetrahedral, which means it has 4 atoms arranged around like this. It's a 3-dimensional structure. So you have 4 bonded, no lone pairs, 0 lone pairs. And so that would be tetrahedral. All right, well, let's do another one. How about if we had, say, how about carbon with 4 hydrogens attached? And this would be known as methane. And so once again, we go ahead and we count up the valence electrons. We look on our periodic table and we see carbon has 4. And the hydrogens, each hydrogen has 1 valence electron. So you can see the hydrogen's in the 1 block and carbon is in the 4 block. And so, but there's 4 hydrogens, so we say times 4, and that gives me 4, and 4 plus 4 gives me 8 total valence electrons to work with. And so once again, carbon is the 1 by itself, so we put it in the middle, and we put hydrogens all the way around. We have 4 hydrogens, so we need to put down 4 hydrogens on our structure. And we go ahead and make a bond. Go ahead and glue them on, 2 electrons being a bond. And we subtract off the 8 electrons we just put down. We have 0 left over. And so once again, we check and see that we have full octets. And the carbon, sure enough, has 4 electrons around it, no problem. It has 4. Well, what about these hydrogens? These hydrogens have only 2 electrons. But that's okay because hydrogen is happy with 2 and boron is happy with 6 and everybody else wants 8. So carbon has 8, it's happy, and the hydrogens have 2, and that means they're happy as well. And we can use a stick drawing here and draw it out. And this one is also tetrahedral. Let's try another one. How about ammonia? Ammonia has a structure that is NH3. That's ammonia. And so we would take the nitrogen and we go to our periodic table and we see that nitrogen is in the 5 column. And so it has 5 valence electrons. We see the hydrogen is 1 valence electron, but there's 3 of them. So that gives me a total of 8. Well, 3 off of this, and grand total of 8. And so we do the same thing. Now, we have to be careful. There's 3 hydrogens, there's not 4. So we only put down 3. And we go ahead and make a bond for each one. And subtract off the 6 that we just put down. We have 2 left over. Now, what are we going to do with those two extra electrons? Well, we can't put them on the hydrogens because the hydrogens are already happy with 2. So we go from the inside, we glued on the hydrogens. We go on the outside. If we have room, we put the electrons out there, but we don't have any room. So we go back on the inside and we put them in as what are called lone pairs. And so it's not bonding, but it is on the nitrogen, and it does count as one of the 8 electrons. And so sure enough, the nitrogen has 8 electrons around it, so the nitrogen is happy. And the hydrogens, well, they have 2 electrons apiece, so they're happy. And so they go back on the inside. And so just to emphasize that they're there and they take up room, we say that that is a lone pair. Now, how would we sketch this out? If we look at our table of molecules, we would see this is 3 bonded, 1 lone pair. And if we look at the molecular structure, this is called trigonal pyramidal. Because if you sketch it out, it actually looks like a pyramid. There you go. So that has 3 bonded, 1 lone pair, and that makes it trigonal pyramidal. It's literally a triangle-based pyramid. Okay, so if you have extra electrons, they go back on the center atom. Now, let's do another one. Show you another illustration here of how you do these. Let's say we have boron trifluoride. Now, we still have to add these up, and we look for boron. Where is boron? Boron's over here in the 3 columns, so we know it has 3 valence electrons. And fluorine, well, each fluorine has 7 valence electrons. You can see on the periodic table that fluorine's over in the 7. And so, but there's 3 of them. This gives me 21 for a grand total of 24. And so once again, let's go ahead and set these out. And we'll go ahead and make our bonds. There's 3 fluorines, so we're going to be bonding with 6 electrons. Let's go -6, and we have 18 left over. And we have room on each one of these fluorines for 6 more. And so we go 1, 2, 3, 4, 5, 6 for a total of 18. So we've put down 18. And so sure enough, we have none left. And now we check for octets. The fluorines are happy. They have 8 apiece. The boron, on the other hand, has 6. But that's okay, because you see, boron is happy with 6. Because remember, everybody wants 8, but hydrogen is happy with 2, and boron is happy with 6. Everybody wants 8 except for boron and hydrogen. And so, sure enough, that's the structure, and we can sketch this out as like this. And if we look on our table of geometries with 3 bonded, no lone pair, this is actually a triangle that sits in the plane, and so we call that trigonal planar for its molecular geometry, the shape that it would actually have. So we look on the table, we see that we have 3 bonded, no lone pairs, and therefore it's trigonal planar. If you have lone pairs, it cannot possibly be planar. So there's no lone pairs, so it is planar. It's trigonal planar. Okay, and for my final example on doing Lewis structures, let's do carbon dioxide, CO2. Go ahead and add up those valence electrons. We've got 4 valence electrons for carbon. And for oxygen, that's 6 valence electrons. And there's 2 of them, so that gives me 12. And that gives me 16 total. So let's go ahead and put down these oxygens. And I'm going to go ahead and put them side by side because I know what the structure is ahead of time. And so go ahead and put down 4 electrons, 2 electrons for each bond. We bonded them in. Now we have 4 electrons left over. And no, 12, pardon me. We put down 4. We have 12 electrons left over. And we have room for 6 more electrons each one of these oxygens. And so let's go ahead and put down the 6 electrons on each oxygen. That would be 12 total. And that would leave me with 0. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Now, when I check for octets, the oxygens are happy. However, look at the carbon. The carbon is not happy. It only has 4 valence electrons on it right now. So what we have to do is we actually have to take and slide in electrons. Now, we're not taking them off the oxygen. We're just going from not sharing to sharing. And so now we're sharing 2 over here. And we'll do the same thing over here. We'll slide these in. So now that they're shared electrons, of course, go ahead and erase it because we moved it. And now we have 8 electrons on that carbon. We still have it on the oxygens. They're still there. Those oxygens still have 8 electrons. 2, 4, 6, 8. But the carbon now is sharing as well in between. So if you look there, the carbon does have 8 electrons now. And since a bond is 2 electrons and now we have 4 electrons, that's actually considered a double bond. And so the actual structure looks like this. And of course, we still have those 2 electrons on the 2 pairs on the oxygens. And this is called the double bond. And carbon dioxide has 2 double bonded oxygens. And if we have 2 bonded 0 lone pairs, well, this looks like a line, and it is. And this is called linear. So keep in mind, though, that these electrons over here, those are not lone pairs. Those are actually called non-bonding pairs. So don't confuse those with lone pairs. Lone pairs, strictly speaking, are on the center atom. They're on the center atom. So there's no lone pairs there. So this is 2 bonded, 0 lone pairs. Okay, and we can do this all day long with different molecules, and I'll give you another example here. Let's say we had let's say we had SO3. Well, that would be sulfur would be 6, and the oxygen lost will be 6. That's times 3, 18, and we have 24. And so we will go sulfur, oxygen, 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 make those bonds. 2 electrons, minus 6, 18. That leaves me room for 6 more on each oxygen. So we'd go 6 more on each oxygen. There's 3 oxygens, so that's 18. And we'll go put my 6 electrons on each one. And so sure enough, we've used up all the electrons. Sulfur needs 2 more, so we'll go ahead and slide this lone pair over here. We're going to slide this over. It doesn't matter which one we pick. It just needs to go in to make sulfur happy. And so we've moved it on in. And so now everybody has an octet. And the structure would be double bonded oxygen with 2 single bonded oxygens. Once again, they do have electrons on them. There we go. And if we look this up, this once again is a triangle that sits in the plane, and this is trigonal planar. Okay, so and that's because we had 3 bonded, no lone pairs. Okay, so as long as you have a table of structures, or hopefully you've memorized the table of molecular structures as far as bonded with lone pairs, you can get the structure. Now, the final thing we need to be able to do is tell whether a molecule is polar or nonpolar. And so before we do that, we have things called polar bonds and nonpolar bonds. Basically, we have something called electronegativity, which has to do with how much how much an atom really wants the electron. And the way the electronegativity goes is the closer you're to fluorine, the more electronegative you are, and the further you are away, the less electronegative. So this is less electronegative out here. Okay, less. Let me change colors here. Well, less electronegative, further you are away from fluorine. And so what that has to do with is how bad does a bond, how bad does a atom want the electrons? And so the classic example is HF. So since nothing can be more electronegative than fluorine, what it's going to want to do is, if we can change this line out into electrons, and we would say, well, it's dead center in between, the fluorine will actually pull these electrons closer to it. If that's the case, well, electrons are negative, and so we end up with a partial negative charge on the fluorine and a partial positive charge on the hydrogen. And so the fluorine end becomes a little bit more negative, and the hydrogen end becomes a little bit more positive. And we say these are poles. These are electron poles. We have a positive pole, we have a negative pole. And so that's what we mean by we say it's polar. So this molecule is polar. It also has a polar bond. Now, the easy way to tell is if you're left to right on the periodic table, then the bond is polar. And if you're up and down on the periodic table, then it's nonpolar, including being the same. So a carbon-carbon bond would be nonpolar, whereas a carbon-oxygen bond would be polar, because if carbon-carbon is the same atom, it's nonpolar. Carbon-oxygen are on two parts of the periodic table, left to right to each other. If you look over here, you'll see that it is, sure enough, it is left to right with each other. And so that's how we can tell if something is polar or not, is generally if it's left to right of each other, then they're polar. If they're top to bottom of each other, they generally tend to be non-polar. And so if we take a look at, say, carbon-carbon's non-polar, carbon-oxygen's polar, and even like a sulfur-oxygen bond would be non-polar. And so generally when we say polar, non-polar, we're also talking covalently bonded, not ionic bonding. All right, so now we have to be able to say, well, whether a molecule is polar or not. And it works like this. If you have a molecule, it can have polar bonds, but not be polar itself. You have to have a net pull going in one particular direction. The carbon fluoride bond is quite polar, but they're pulling this way. And so the carbon fluoride bond is polar, the CF bond is polar, but they're all pulling equally away from the carbon. And so the whole molecule is nonpolar. It's a nonpolar molecule. However, if let's take a look at, say, ammonia, on the other hand, with its lone pair, the nitrogen is more polar than the hydrogens, and so we're pulling this way towards the nitrogen. And so the net push, the net pull, is going to be facing this way. And since it's pulling towards the nitrogen end is going to be partially negative, and the hydrogen end is going to be partially positive, because there's a net pull going in that direction. And we can take a look at one more molecule. Let's take a look at, let's say, carbon dioxide. Well, let's look at two more. Carbon dioxide, same deal going on here. We're pulling opposite of each other towards the oxygen, which is more electronegative than the carbon, and so the overall molecule is nonpolar. And finally, let's take a look at one more molecule. Let's take a look at boron trifluoride. And the fluorines are quite electronegative. We're pulling in that direction, and the whole molecule is nonpolar. Now, for small molecules, it's rather, there's an easier way than trying to draw arrows, and that is if it's the same thing all the way around, it's nonpolar. And if anything's different, it's polar. So this is the same and different rule. And if you look at the carbon tetrafluoride, it's the same all the way around. So sure enough, it's nonpolar. Same thing with the carbon dioxide. It's the same all the way around. It's nonpolar. Over here, we have the same all the way around. But look here. We go hydrogen, 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 and a lone pair. A lone pair is not the same as the hydrogens. Not the same. And so ammonia is polar because it's not the same all the way around. Let's take a look at say water. Water has two hydrogens and an oxygen. It also has two lone pairs. I like to say the water looks kind of like it's got bunny ears. So is water nonpolar or polar? And if you look around, you see that hydrogen, hydrogen, hydrogen lone pairs, this is not the same. So water is very polar. And it's very polar because it has hydrogen bonding, which is the OH. Okay, water is very polar. It's also bent. If you look at it, it has two bonded, two lone pairs, and therefore it's bent. And if you look, it's not straight at all. It is bent. And so water is bent molecule. It's very polar. And if you look at it, it's not the same all the way around. And even if you didn't look at that, you would say, you know, it's drawing towards the oxygen, and you're going to point this way with the partial minus on that end and the partial plus on that end.